Hi, everybody. It's Professor Mitchell, continuing with Chapter 10. Today, we're looking at Section 10.3 on the integral test. Remember, throughout this chapter, we're talking about tests to determine whether infinite series converge or diverge. All right, so let's start with talking about non-decreasing partial sums. And let me first remind you what Theorem 6 said. This was a theorem from section 10.1, and it said that every sequence which is non-decreasing and bounded from above converges. All right, it said something a little bit more general than that, but that's the only part we need. So if a sequence is non-decreasing and bounded from above, the sequence converges. So to turn that into a useful fact about series, we have this corollary. A series of non-negative terms converges if and only if its partial sums are bounded from above. All right, so as an example of using that corollary, we're going to look at the so-called harmonic series, the sum going from n equals 1 to infinity of 1 over n. This is a very important series. We refer to it a lot. And I'm going to switch over to my tablet where I've already got all this worked out. And I will talk through it with you. Okay, so here is the series, the harmonic series that we're talking about, and I've written out quite a few of the first few terms. So of course it goes 1 plus 1/2 plus 1/3 plus 1/4, et cetera, et cetera. And by the way, this is one of those things that I did not think of myself and probably would not have thought of myself. All right, somebody showed this to me back in the day. I think this is a very clever way to establish what this series does. I don't want to spoil it, and please don't look down. All right, so what we're going to do is we're going to group the terms of this series in again, a clever way. So we're going to leave the 1 plus 1/2, and then we're going to group the 1/3 plus 1/4, and note that those two terms are greater than 1/4 plus 1/4, which is 1/2. And the reason for that is that 1/3 is greater than 1/4. Then we're going to take the next four terms, 1/5 plus 1/6 plus 1/7 plus 1/8. Note that all of those terms are greater than or equal to 1/8. And so those four terms add up to something which is greater than 4 times 1/8, which again is 1/2. And then we're going to look at the next 8 terms, 1/9 through 1/16, and we'll note that all of those terms are greater than or equal to 1/16. And so the sum of those terms is greater than 8 times 1/16, which is again 1/2. And in general, the partial sum s sub 2 to the k, take a moment to wrap your head around that notation. So that is the 2 to the kth partial sum. In other words, we're only looking at partial sums S1, S2, S4, S8, S16, where the index is a power of 2. And what we've shown here is that in general, the partial sum s sub 2 to the k is greater than the number k over 2. Since the sequence of partial sums is not bounded from above because it's greater than k over 2, s sub 2 to the k is greater than k over 2. By the corollary to Theorem 6, the series, the sum n equals 1 to infinity of 1 over n, diverges. It diverges. So I want to point something out to you at the very end of section 10.2. Maybe it wasn't the very end, it was close to the end. We talked about the nth term test, which said that if a series, if the nth term of a series is not approaching 0, then the series diverges. So this is a great example of why the converse of that theorem does not work. The nth term of this series is 1 over n, And of course, that does approach 0 as n increases without bound. And yet this series diverges. It does not converge. So once again, please, 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 please do not ever say that since a sub n is approaching 0, that means the series a sub n converges, because it ain't necessarily so. All right. Okay, so let's start talking about the integral test. The question here is, does the series sum n equals 1 to infinity of 1 over n squared converge? So we were just looking at the series n equals 1 to infinity 1 over n, and we decided that that series diverges. Okay, so we've got this picture here, and I'm going to switch back over to the tablet in just a second. So notice this first rectangle whose area is 1 over 1 squared. I'm going to kind of pull that aside and treat it separately. What I want you to do is look at this graph of f of x equals 1 over x squared, starting at x equals 1. And notice that these smaller rectangles, starting with 1 over 2 squared, all fit under that curve. All right, so what I'm trying to set up here is an inequality that compares the value of this series, the sum of this series, if there is one, to the value of an improper integral, All right, so I think I'm ready to go over to the tablet. So what this picture shows is that the sum of the series n equals 1 to infinity of 1 over n squared is less than 1, which was the area of that first rectangle, plus the integral from 1 to infinity of 1 over x squared dx. Let me switch back to the presentation for a second, just so we can make that clear. Okay, so the series, the value of this series is represented by the sum of the areas of all these rectangles, including the first one. And what we're saying is that that is less than the area of the first rectangle plus, let me see if I can bring up my pen here, plus the area under this curve. This is going to be really sloppy, which includes all of these smaller rectangles and also a bunch of stuff above the smaller rectangles. I am not very good at coloring inside the lines. Hopefully you can see what I'm trying to do here. All right. Okay, so let's go back to the tablet so I can finish this off for you. Okay, so the sum of the series, if it exists, is less than 1 plus the value of this improper integral. And now I'm just quickly going through the calculation of this improper integral. You remember how that works from section 8.8. And it turns out that that this improper integral converges. It converges to 1. So that shows that this series converges. It converges to something less than 2. And I'll tell you a really fun fact, which I actually don't remember how to prove if I ever knew it. It is actually known, I'll just put this in a little fun fact box here. It is actually known that the series n equals 1 to infinity 1 over n squared converges to the number pi squared over 6. So this is just one of those surprising facts. The number pi creeps up in all sorts of unexpected places. And you can check on your calculator that pi squared over 6 is in fact less than 2. Okay. All right. So couple of things we accomplished with that example. Number one, we show that this series converges. And number two, it kind of suggests how the integral test is going to work. All right. So here it is. The integral test says that if a sub n is a sequence of positive terms and a sub n is equal to f of n, where f is a continuous positive decreasing function of x for all x greater than or equal to some positive integer, then what you can conclude from that is that the series n equals that number n to infinity of a sub n, and the integral from capital N to infinity f of x dx either both converge or both diverge. So the idea is take your series and look at the corresponding improper integral, and using the methods of section 8.8, determine whether that integral converges or diverges. And then as long as these conditions are all met, that the function is continuous, positive, and decreasing, then your series will do the same thing that the integral did. Okay. All right, so a first use of that of this integral test is for, I remember one of my undergraduate professors called this the P test or P series, and I'll probably refer to it the same way. For what values of P does the P series, series n equals 1 to infinity of 1 over n to the P converge? Switching back over to the tablet. We can do this pretty quickly if we refer to a fact that we developed in section 8.8. The series n equals 1 to infinity of 1 over n to the p converges if p is greater than 1 and diverges if p is less than or equal to 1 by using the integral test with the integral 1 to infinity of 1 over x to the p dx. So we spent a little bit of time in section 8.8 showing that this improper integral converges if p is greater than 1 and diverges if p is less than or equal to 1. So the corresponding series does the same thing, and we will make frequent use of that fact. All right, so let's see if I can get my mouse to work here. We will go back to, had to click on it about 5 times. It still thinks I want to use my pen. Okay. All right, so now we get to some examples, and I think these examples will keep us busy for the rest of this section. In the first 2 examples, we're going to use the integral test to determine if the series converges or diverges. And we need to check that the conditions of the integral test are satisfied. So I will talk you through those. Here are the 2 examples. And then to warm you up a little bit for what's coming, for example, when you take an exam that includes this chapter, they simply ask, does the series converge or diverge? And they don't tell you what test to use. So I'm going to kind of talk you through recognizing what might be a good test to use. All right, so back to the tablet one last time. Starting with the series n equals 2 to infinity, 1 over n times the natural log of n squared. All right, so we are going to let f of x equal 1 over x times the natural log of x squared. And we need to check 3 things. First of all, that this function is continuous. Well, it's continuous as long as x is not 0, which it won't be because we're starting the series at n equals 2. And also as long as natural log of x is not 0. The only time natural log of x is 0 is when x is 1. So again, we don't have to worry about that because we're starting the series at n equals 2. So this function is continuous. Next, is it positive? Well, yes, because again, we're starting the series at n equals 2. So of course, x will be positive. It'll be at least 2. And because we're squaring the natural log of x, I don't even have to think about the possibility that natural log of x is negative, which it won't be anyway. We're multiplying x, which is at least 2, by something squared. So that is definitely going to be positive. Usually the thing that takes the most time to check is the decreasing part. That's not going to take a lot of time in this example, but it will in a couple of the other examples. So I'm going to say that f of x is decreasing because its denominator, x times the natural log of x squared, is increasing. Okay. Especially once natural log of x becomes positive, which happens at x equals 1, then natural log of x is an increasing positive function. And so when you square it, it's still going to be increasing. Excuse me. So all of the conditions of the integral test are met. So now we are going to look at the integral 2 to infinity of 1 over x natural log of x squared dx. All right, and I think it might be a good idea to start by getting the antiderivative for 1 over x natural log of x squared. And then it makes the notation, a little bit less clunky, less things to carry around, or at least not have to carry them around for so many steps. All right, so integral 1 over x natural log x squared. That is a u substitution. If we let u equal natural log of x, then du is 1 over x dx, which means that the integral 1 over, excuse me, x natural log of x squared is going to be equal to 1 over u squared du. Okay, so that's a nice simple integral. That integral is equal to negative 1 over u plus c, but it's not about u. U was natural log of x, so this is negative 1 over natural log x plus c. So now I'm ready to talk about this improper integral. Remember how this works. Integral 2 to infinity of 1 over x natural log x squared dx is equal to the limit as b approaches infinity, integral 2 to b. Okay, and now since we've got that antiderivative handy, we can just go limit as b approaches infinity, negative 1 over natural log x, plug in b, plug in 2. All right, so we get negative 1 over natural log b minus negative 1 over natural log 2. And as b increases without bound, 1 over natural log b approaches 0. This limit is 1 over natural log 2. This integral converges to 1 over natural log 2. So what I'm going to say is, therefore, the series n equals 2 to infinity, 1 over n natural log n squared, converges by the integral test. Okay, and I want to point out that we have no clue what this series converges to. That's one unfortunate thing about the integral test. It tells you what the corresponding integral converges to, but that doesn't give you any information whatsoever about what the series converges to. Unfortunately, it doesn't even tell you most of the time does the series converge to something less than 1 over natural log 2, greater than 1 over natural log 2. We just don't know. Okay. All we know is that it converges.